Hi, everyone. My name is Martin Laprise. I'm the chief scientist at XTKI. So we worked with Celestron for the last years on the Origin project. So we're super happy to talk about the AI technology deployed on that scope. So I'm going to share my presentation here. Okay. So I just want to make sure that everyone that using the Origin telescope have a good sense of how things works under the hood. We don't want to make a black box. We want to explain the technology that we built in there. So that's what we're going to hear. A good part of the talk is to present the AI component of the solution. And first, I want to step back a little bit and talk about what we mean by AI anyway. So there's a lot of AI these days. Journalists talk about that. It's often a little bit hard to know what it is precisely. And also the definition changed quite a bit over time as well. So it's not always easy to know what it is clearly. So AI is essentially, it's a software that learns by example. And this is pretty much the definition I'm always using. And what I mean by that is that when we're developing classical software, the developer, what they'll do is they will identify some problem that they want to solve. They will break down those problems into subtasks, and they will encode or code explicitly those tasks into the software. And that's the way most of those software is still done these days. And it works quite well, but sometimes there's some specific tasks that are quite hard to hard code manually. So for example, if I want to detect if there is a cat or a dog in the images, yes, I can just try to come up with some heuristic that find the ears and the whisker and the color, stuff like that, and to identify the dog. Or I can set up an AI model. And what we mean by the AI model is some kind of a template of a program that we specify the goal that we want to achieve, and then we present the program some example, and the program, the AI model will learn the instruction by itself. So that's in a high level what we mean by AI model. For example, if I'm a Tesla or like a car manufacturer and I want to detect car on the road, what I'm going to do is I'm going to set up an AI model. I'm going to provide some example of car. I will annotate those images, and I will train the model. And when the model is trained, then I can deploy that model on my car, and I can do prediction live on my video stream. So that's pretty much the most popular AI model that runs these days. And those models are what we call deep learning model, and that's the best way to do AI model these days. There's also a lot of talk these days about large language model, and large language model in a way are trained the exact same way. So you take a template of a program, a deep learning neural network, and then you feed that neural network with a bunch of text, and you ask the model to predict the most likely text given a specific context of prompt. And when your model is trained, you can just deploy that in an application like ChatGPT. You can ask a question and it will output some text at the output. The trend we're seeing lately is that most of the software these days are made of classic software development, a lot of that. But there's also more and more place are taken by AI model. And when we design the imaging pipeline of the Celestron Origin, this is what we had in mind. We want to, yes, do the best we can for each one of those steps using classic software development. But if there is some part that we feel like AI model can be leveraged, we want to leverage that essentially. So for most people used to astro imaging, that pipeline will look familiar. There's nothing super exotic about that. So I won't go into each one of those details in this talk. I will focus more on some of the AI approach that we took in the pipeline. So more specifically, I want to talk about the acquisition part, and then the later part at the end, the deconvolution, the denoiser, and the gradient removal. So like I said, there's nothing super exotic about the pipeline, but the Origin telescope has some unique aspect, and I want to make sure that we know those unique aspects. So the first obvious one is the fact that the Celestron Origin is an AltAz telescope, so there's no equatorial mount, so that's why it's so simple to use. But on the other hand, it means that we need to take shorter image exposure, and we need to design the pipeline so that it can handle that optimally. So that's one thing. And then another thing that are specific to the telescope is that the imaging processing task pipeline need to adapt to any situation. Like if someone is taking an images, we want to output the best process images at the end. on the application without too much intervention. So the software need to adapt automatically to the real condition. And all of those things need to happen in real time. So since the sub-exposure are 10 seconds or 15 seconds, we essentially have like a budget time of 10 seconds to do all of those things. So because we want to provide a refresh update every 10 seconds. And all of those things need to happen on the embedded computer, the Raspberry Pi, as well as the mobile app. So that's some of the challenge that we need to address. But the good thing is that we have some benefit. The Celestron Origin is a really well-known platform. We know all the spec. We know the aperture, we know the mount, we know the sensor. So what it means is that we can really optimize the imaging pipeline specifically for that scope. So the pipeline is custom C++ code. It was written by the Celestron's team for the entire scope. We help them work on the imaging stack. So it's super fast and with really small memory footprint. So quick reminder of the spec of the scope. The Celestron Origin is a 6-inch Raza scope, f2.2, super fast. We can just acquire images much faster than the other telescope out there. It's a Sony sensor using back illuminated technology, which means that there's a really low C readout noise. And the compute is a Raspberry Pi 4 coupled with the chip on the application side, either iOS or Android. So now I want to go back a little bit on the acquisition. If we remember the pipeline, this is the first step in our journey, essentially. We need to make the exposure using the camera, and we need to do the acquisition. Now, like I mentioned, one of the specificity of the scope is that it's in AltAz mode. So normally, if you read about astroimaging, the first thing they will tell you is, oh, hey, you need to buy a equatorial mount. That's the first thing to do because we want to track the sky perfectly for super long exposure. So that's not what we're doing here. The Origin scope is AltAz, and what it means is that it's super easy to use. You can just put the scope level out there and it will figure out by itself what's to do and what it is in the sky. So, but on the other hand, what it means is that when the scope is following an object, the object will rotate into the field of view. So that's a challenge that we have. Again, if you read about astroimaging, the first thing they will tell you is that, hey, you need to take 5-ish or 3-minute exposure. That's the optimal time. Because in our case, we can do that. We are limited to 10 or 15 seconds. So the question is, where did this come from? Normally, in a classic solution, we want to take long sub-exposure is to lower the total noise in the images. And to understand that, we need to go back to the physics of astroimaging. And all those details, by the way, I really recommend the Robin Glover talk, which is really, really an extensive overview of those topics. But here I was going to do like a quick explanation. Essentially, everything in astroimaging is all about noise. It's like that's pretty much the reason why we take long exposure. That's the reason why we have big aperture. That's the obsession with astroimaging, is to increase the signal ratio, the signal to noise ratio. And when you look at the physics of this, at the beginning, the whole point of the CMOS sensor is to take a photon, incoming photon, and convert that photon into an electron. And that electron will be picked up by the analog amplifier and converted into the digital signal that we're using in our computer. So that's the first step. Photon is converted into electron, but the reality is that at room temperature, with enough heat itself can make the electron move, and that will create what we call thermal noise. So that's the first source of noise in an imaging is thermal noise. That thermal noise is random, but there's also like a fixed pattern on the chip. So that fixed pattern can be handled correctly with the dark calibration that most people know about. And the thermal noise, the normal way to handle that is to lower the temperature of the sensor. Now, another source of noise in the CMOS sensor is what we call the ring noise. Like I mentioned, every time a photon hits the sensor, it would convert into an electron if the quantum efficiency is perfect. And then the analog current converter will pick up that current and then create a digital signal with this. And that process is not perfect. Sometimes there's a little bit of noise in this conversion, and this is what we call the ring noise. So essentially, every time you read data from the CMOS sensor, you're adding up some of those ring noise. And if you look at the total stack noise in the final images here, you can see that it's the ring noise is multiplied by the number of subs that you take in your images. So really, ideally, what you would do is take a single 1-hour images, and that would minimize the ring noise. So as you know, it's not super handy to do that. tracking the sky perfectly for 1 hour is super hard, and you just increase your chance of having some defect in there, like a plane or like a Starlink satellite, something like that. So that's not what we do. So people usually end up using like 5 minutes or something like that as optimal way to manage that. As you will see later in my presentation, like the re-noise in our case is not the bottleneck, so that's not an issue. But next, the other source of noise are light pollution. The light pollution is a way act as noise on images, and in most scenarios, that's the dominant factor. And lastly, the last source of noise is the shot noise, the actual photon itself coming from the object. They're not coming at a really specific fixed rate. So that jittering essentially is what we call a shot noise. And in order to decrease the shot noise, there's nothing you can do except increase the total exposure time. Like I said, the signal to noise ratio will increase over time. So the more you add a sub into your total exposure, the better the signal will be. So you can see in the images here, we took multiple exposure using the Celestron Origin telescope, and we can see like the progression of the signal to noise ratio. And the signal to noise ratio is proportional to the square root of number of sub, essentially. If we look at the definition, like the total noise in our images, we can actually compute beforehand the total noise that we'll see on each one of those pixels. Like this is the number of sub multiplied by the real noise plus the pollution, the noise for the light pollution. And if we compute that with all the specific attribute of the telescope, like we know, for example, that we are in the bolder sky, it's really dark, the quantum efficiency, the pixel size, and we put in all those metric, all those specifications into the equation, we end up with a graph like this. So this graph essentially is showing the total noise per pixel for a fixed total exposure time. So let's say, for example, I want to take a 1,000 second total exposure of an object. I have multiple choice. I can either do, in extreme case, 1,000 sub and stack them, or like I can do like a single 1,000 second sub. And here we can see the total noise varying across all those scenarios. And as we can see, the less sub we're using, the less total noise we have in the images. But also another takeaway from that images is that, yes, the total noise is decreasing, but below a certain point, like around 10 or 15 seconds, there's not that much difference, essentially. Really, because in most scenarios, most of the noise is dominated by light pollution. And even the thermal noise on most modern sensor, it's really quite low. And this is for a border 3 sky, and if you are a border 5 skies, it's even worse. So, so the takeaway is that using sub, a really quick sub, in our case, is not a bottleneck at all. In fact, it's a benefit because it allows us to better track the sky. It allows us to skip some of the sub if something happens. If some Starlink satellite go across the scope, we can just remove that. And also another takeaway is that there's nothing we can do except increase the total sub exposure time or use some kind of a denoising, because really like the images is dominated by light pollution. And one thing I haven't mentioned is that, yes, the light pollution will also increase with total exposure time, but it will increase at a lower rate than the actual signal. So that's why it's always beneficial to take longer exposure, even if you are in Tokyo, let's say. So, but one thing we can do is try to figure out a way to reduce that. The RASA design is super fast, but which means that we don't have to wait like 3 hours to get a nice images. But if you can push that even further using some kind of AI denoising model, that would be great. So that's the first model that we work on the pipeline. And essentially at a high level, the way that we design the model is using some kind of adversarial training loop like this. So we have the Celestron Origin images. We took images that were really low noise. And then what we did is we actually model the CMOS noise of our sensor, and we add that noise artificially to the image, and then we ask the model to remove that noise. And then at the end of the process, we compare the actual clean image with the denoise image, and we train the model this way. And this is how we train the model. And also, like, one really specific aspect of the deep learning that we develop is that you need to run on a phone. So that's quite a bit of a challenge. So it's really well optimized to run an Apple neural engine on the iPhone and on the ARM-chip instruction on Android. And one thing that is interesting, there's other solution that can remove noise using AI model, but in our case, what's really interesting is that we actually train the model on deep sky images by Celestron Origin, and we also use the actual CMOS noise of our sensor in order to train the model. What it means at the end, combined with the aperture of the RASA with the denoiser, you can see images really quickly. That's an example where we take an images and we apply the denoiser on that images. So this is just a few sub on the Whirlpool Galaxy. If people go to the app, they'll see that in the advanced setting of the app, they can actually control how the denoiser is working. So they can disable that entirely if they want, but they can also change the amount of denoising done by the app. They have like low, middle, and high, so people can just control the way it works. So that's the denoising model. I talk about denoising because that was the first one that we did, but really in our pipeline, we're actually starting with the deconvolution. So now we'll talk about the AI deconvolution model. So that's an images of Crab Nebula, and here I did like a zoom on this star, and for most people this is a star, but for me this is not a star. This is a point spread function of the telescope. So essentially what I mean by that is that every telescope have a response to a star. Like a star in a way is a really infinitely small point in the sky. So technically, if you image the star using a perfect telescope, using a perfect camera, you will end up with a really small pixel on your images. But in reality, what happened is your star is spread out essentially by the scope and the aperture of the scope, by the camera, everything. So that response of the telescope is what we call the point spread function. And here, for example, I simulate what the point spread function would look like to a telescope similar to RASA. This is not the actual RASA telescope design, but it's really similar, like it's a really similar aperture. So here, for example, we can see the 6-inch aperture with the secondary mirror, and we even add the camera cable here. And if we model the point spread function of that aperture, it would lead to a point spread function like this. So we can see the classic sync function of the diffraction pattern. For every astronomer out there, they will know that it's really rare that you see that in the sky, simply because there's a lot of turbulence, and the turbulence will also add up and do like a compounding effect on the point spread function. So that's an example where we simulate some cell in the atmosphere that will affect the turbulence. So another thing about the turbulence is that obviously it's not fixed during time. Like there's a lot of changing condition in the sky, and in reality, when you look at the star, like really zoomed in, you will end up with something like this, like a moving point spread function, essentially like a moving response. And at the end, when we take images, we averaging out all of those effects together and we sum them into the images. In reality, it's even worse because there's also like the defocus, like the image is never perfectly focused. If you go to the outside of some scope, for example, sometimes you have field curvature, so some of those stars at the periphery of the scope won't be focused properly, and those defocus will also affect the point spread function of the scope. So at the end, what we have is like a big blob of all of those effects integrated over time, and that's what we see as a star. Essentially, that point spread function is pretty much the response of the imaging system to an infinitely small light source. And in reality, your images, if you want to see like the effect of the point spread function of your images, you take that point spread function and you apply that on every one of those small pictures here. Like you scan through the entirety of the field, and this is what we call a convolution. So really, like the end images is a convolution of the point spread function with the input images. So that's what we see here. Now, the good news is that there's some ways to revert that effect. Like we can just take the convoluted images, the image that we actually see on the sensor, and if we know the point spread function, there is some method that exists to somehow guess the actual origin image, like the image at the input of the system. So if you use any popular software in astronomy, you know recursion Lucy, that's one example. There's also the Wigner algorithm that allows you to do that guess, essentially to do that opposite direction processing. Now, those methods works quite well, but there's a lot of limitation to those iterative methods. First of all, like I mentioned, you need to know the punch thread function. That function here, you need to do that perfectly in order to do a good job using those iterative methods. Another thing that is always hard in real scenario is that the punch thread function is quite complex. Like previously, I showed like some interesting response of the aperture and the atmosphere. But in reality, the point sprint function is really complex, and it's not always easy to model that carefully. Now, the good news is that in astroimaging, we are lucky because we have a whole bunch of point sprint function across the images. All the stars are essentially like a good estimate of the point sprint function. So we can use that as a proxy. But another limitation that we have is that those point sprint function are not the same across the field. So, for example, in a cheap refractor, you're going to see at the edge of the refractor, there's a lot of aberration. In some kind of reflector, you're going to see like spherical aberration in the edge of the field of view. And really, like when you're doing like a deconvolution using a classic software, there's nothing you can do about that. You can just guess the point sprint function and gonna try to restore the entire image using the same setting, essentially. So that's a limitation. Finally, the method is not aware of the object, like it's just going to guess what the object would look like, but you can just add distortion or like artifact around the images and it won't be penalized for doing that. So that's why we develop an AI-based deconvolution. And I won't go back to the way we train it because it's actually quite similar to how we train the denoiser. But essentially, like we model the point straight function of the scope, and then we generate example that the model can train on. Like here's an image at the input of the scope. We actually apply the point straight function to the scope on that images, and then we ask the model to restore the input images. And then we do that for like weeks, essentially, until the model is properly trained. And so this model have multiple benefits. First of all, the model will take the images at the input and output directly the deconvoluted image. Like there's no like multiple iterative step. And in our case, as I mentioned before, since everything is running real time, we don't have that luxury of using recursion Lucy in real time, for example. So we need this to run really quickly. So that model can do that. The model also is specifically trained on Celestron Origin images. So we know that it will work better because first of all, we model the point sprint function of the scope, but we're also using real images took by the scope in order to train the model. Finally, the model also have like the benefit of essentially model a really complex point sprint function, and it can also use different point sprint function across the images. So if, for example, I put a lot of small patch on top of the images, and we can imagine the system, the AI model will look at each one of those patch individually, and it will apply really local correction. So that's a big benefit. So I'm not sure it will come across correctly on YouTube, but you can see the effect on this galaxy, for example. One thing I want to mention is that the deconvolution model won't create or invent any detail. It will only enhance the detail that are already there. So that's something that I really want to make sure everyone understand, like, because we are seeing a lot of generative AI these days that pretty much invent images from scratch. And that's not what we do here. Here, we actually train the model specifically, I would even say scientifically, to deconvolute image from the Celestron system. And then the only thing we're doing here is to revert partially that effect in order to enhance the detail. So that's essentially like where we at in our pipeline so far. So this is the raw image right after acquisition. We do a first stretch of the histogram. Then we do a denoising. And then finally, we do the deconvolution. A good takeaway here is that the denoiser and the deconvolution won't create detail. Like if a detail is not there, there's nothing we can do about that. It will only enhance the detail already there. And in order to understand that, we can actually look at the modulation transfer function. And essentially, any astro images can be seen as a mix of a lot of detail with various spatial frequency, like really large and really faint, really small spatial frequency. And if you have like a perfect imaging system, the system will essentially won't affect the distribution of those frequency, and it will pretty much be like a straight line at the top here. In reality, that's not what happened. Like any system have some kind of a limit. Like even if you have like a perfect telescope, the fact that the scope have a finite aperture, it will introduce diffraction, and only that diffraction will affect the MTF curve, like the modulation transfer curve. And the modulation transfer curve is the equivalent in the frequency domain of the point-spheric function that I mentioned before. So that's the same thing, essentially visualized differently. And you can see here, even for a diffraction limit telescope, the contrast on the really high frequency detail will be affected by the diffraction. In a real scope, it would be even worse because of the various aberration and pixel size and stuff like that. So when we do a deconvolution, what we're doing essentially is we increase the contrast of those small details. So that's what we do. Another takeaway from that image is that some of those detail will be lost into the noise. Once the detail is below the noise floor, there's really nothing you can do about that. Like even the deconvolution won't be able to restore perfectly an image. So that's why it's not magic. Like you can, if you want really perfect images, you need to go to space essentially, or like have a sensor with like infinite dynamic range. So that's not the case. But yeah, that's a takeaway here, is that the denoising and the deconvolution works together essentially in order to increase the detail. So that's the deconvolution model. So the last step that we're doing in the pipeline is the AI gradient removal. And as we can see here, there's already like a first step of gradient removal on the scope during acquisition. If I remind us like the actual pipeline, we do the acquisition, we do the calibration using the dark and the flat in the bias file. We do the registration, like we actually find the star and images, we align them, and then we stack them together. Then we do the raw processing. We convert that image into color image. Then there's a first step of gradient removal on those sub. Then we stretch the histogram. We do a background neutralization to get a realistic color. And then we pass those things into the AI models. And at the end, we do another pass of AI gradient removal. So here's a typical images taken in the city. Like you can see that it's a little bit noisy. Dumbbell nebula is quite visible because we stretch the image quite a bit, but we can also see like a lot of illumination at the bottom of the images. And that kind of gradient in images is really, really common. Pretty much everyone out there are near a city in some way. We always see some kind of a gradient like that. You can imagine like the city at the bottom here, it will induce a gradient like that. And the more we stretch the image, the worse it is, essentially. So we want to undo that automatically. And the classic way to do that is actually a way that we're doing in the scope as well, is using such really like small sample and try to guess what is the background of the sky using small patch of sky spread across images. And once we have those samples, we can just, using polymer fit or like a spline fit or something like that, we can just reconstruct the background. And once we have the background, we can remove that from the images. Now, a critical piece of that technique is the statistical method they're going to use in order to tell apart valid patch on invalid patch, essentially. Because obviously, if I'm taking a patch around a star, like I will bias the system, like it won't be a valid background. So that statistical test is really like the secret sauce of most gradient removal method out there. And there's a multiple way to do that. We have our own way to do that. That's essentially the first step that we're doing. Once we have that background, we can just remove that, and we can end up with a clean image like this, which is much more appealing. So this is an example where it's quite easy actually, because the object is quite small. It's right at the center. The gradient is quite simple to model, but the reality is that it's not always possible to do like a modeling this way. Sometimes we have an object like this, where the object is taking the entire frame of the camera. And in this case, it's really hard actually to take valid sample of the background of the sky. So, because obviously almost the entire right section of the images here is the object. So, and there's a lot of big star and nebulosity. So it is possible to like came up with some statistical method to just sample the relevant part, but it's not always possible. And even if you do that, the actual model that you can, in order to simulate the background, the spline or the polynomial fit, we won't be able to model the background essentially, because sometimes it just varies too quickly. So that's why we came up with another complementing model that run in the app as well. And it's AI-based gradient removal. And it's based on the deep neural convolutional network like the other one we mentioned. But here what we did essentially is we train a model to remove directly those gradients that we don't want. This is what we call an image-to-image model. The input of the model is actually the entire image. We take this entire image, we feed that to the model, and the output will be directly estimated background. So now the question is how do we train it, essentially? How can the model tell apart the actual object from that nebulosity? So if you look carefully, like a trained eyes will know that, hey, that nebulosity here is like, first of all, it's white, like there's no color, and it's in the corner. So there's a pattern here. And what we can do is during training, we can simulate all those artifacts. Like we can just take a perfect images and then essentially like build up and invent some problem and then tell the model, hey, try to remove that. And over time, as we train the model will be able to tell apart what is a astro object and what is a background. And obviously it's not perfect. If there is, for example, some nebulosity in the corner and that nebulosity is red, like H-alpha, like obviously like the model will struggle a little bit to remove that. But the reality is that most of the time, those gradients, at least why they're ugly, is because they're not the right color. Most of the time they're green or yellow or stuff like that, and they are in an odd place in the images. And if you train hard enough, you will be able to tell apart those things. But it's not perfect. I would say like from all the model that I've shown, this is the most difficult one because there's no hard truth about that. Sometimes those two to merge together. So here, for example, you can see like this small gradient in the corner here. We put that images at the input on the model and we'll output this estimated background. And then we can just remove that exactly like we did with the spline method. So those two methods works together essentially. And we decide like dynamically which one is we need to use essentially. And that's the last AI model running on the stack. And yeah, so we went through the entire pipeline. So that's what's running right now. So like I mentioned, if you have any questions, feel free to ask those questions in the QA section of the team app. I'll try my best to answer them. So the question is, will you continue to collaborate with Celestron on the future enhancement and upgrade? And yes, definitely. So just last week we pushed an update. So right now we're working with Celestron since the beginning on this and monitoring really carefully how people use the telescope. We'll look at the critique and the forum and all of those things. And if there's some improvement we can do, we'll definitely do that. So for example, the denoiser and the deconvolution model is something that obviously the more example you have, the better. And so you can just train, the more example we can feed that, the better it would be. So this is something that we will mostly work on.
I think Chris had another question also, if you click on there. He said, so gradient removal is done 2 times in processing before and after stretching?
Yes, exactly. So on the scope, when we actually acquire a sub, we're doing a first step of gradient removal. And the reason is, if we have a really strong gradient in the images, first of all, the fact that we can remove the gradient on a single sub make the task easier. Because if you can imagine that you have, like, for example, a gradient in the sky because of the city far away on the horizon, and the field of view is rotating, that gradient will change place during the exposure of the image. So if you take, for example, 1 hour images, the gradients will rotate relative to the object. So at the end, it makes the gradient removal a little bit more complex. But if you're working on a single sub, the task is actually easier. And also, like, removing the gradient in the sub also help the later stage in the pipeline. It will help stacking. It will help compensate for the rotation artifact. It will help for a whole bunch of things. So that's why we're doing that at that stage. And then at the end, we're doing another stage AI-based, essentially, that look at the end result of the stack images and then remove the grid on there as well. But if you're downloading the final stack raw, for example, that raw will have the first stage of grid and removal apply, but not the latest one. And by the way, speaking of final raw, I know that it's something quite popular. People just download those TIFF raw and just process those raw themselves. The method that I just described, the denoiser and the deconvolution, they only happen on the process image from the app. So if you're downloading the raw, those processes are not applied. So that's why if you open them, they will be much more noisier. They will have like some kind of artifact. The detail might be bigger, like the star will be slightly bigger, the resolution not as great as the output of the iPhone app. Yeah, so also WATS method is used for color calibration, similar to the conventional background extraction model. When we're stretching the images, we make sure that the background of the sky is neutral. That's pretty much what we're doing. So most of the time it's working quite well, but in some edge case, it might, obviously people these days use, for example, colorimetric method on pics inside or like serial or stuff like that. This is something that we can't do because we don't have access to the internet, so we can pull up those stars and then do a calibration like that. So the best we can do is look at the object and try to neutralize the section of the sky that we know should be neutral. So that's what we do. Cool, thanks for joining. Hope you enjoyed the behind the scene of the AI processing origin. We have like a blast working on this. If you have any feedback, please share with Celestron and we'll continue to work to make Celestron even better. Thanks again and clear sky.